Good afternoon, everyone. So in this lecture series, we'll be focusing on the JEE 2024, right? April session. We'll be starting chapter-wise series for all the chapters, right? So we'll be starting with the first chapter, that will be the current electricity, right? So we'll be discussing some of the important questions or the most expected questions from JEE means, right? Based on the JEE means session 2024, right? Now let's begin with the first question here. The question is that current as a function of time is given as 2 plus 40, right? The current is flowing through a wire for 2 seconds, and we have to find the amount of charge flown through the wire, right? So there are two ways to solve this question, right? One way is to solve this question using the graph. Another way is to solve this question using the integration, right? Now, let's focus on both the methods, right? Let's solve this question using both the methods, right? Now we know that the current is defined as current is nothing, that's I, that's equal to dq over dt, right? It's the rate of change of charge with respect to time, right? That's dq over dt. This is the current flowing through the circuit, right? Now, if we integrate this current with respect to time, we will get the total charge, right? Integrating current with respect to time, we will get the total charge flowing through the circuit, right? That's TQ, right? If we integrate it on both sides, we'll get the total charge flowing through the circuit. That will be equal to the delta Q. So delta Q here is the charge flowing through the wire or charge flowing through the circuit, right? Now with the proper limits T1 to T2, right? So this is one way. This is one way of calculating the total charge flowing through the circuit, right? So delta Q will be equal to, that will be integral of IDT, right? Integral of IDT. With the limits, we have been asked to find the charge flown through the wire for the time 2 seconds, right? We'll integrate it from 0 to 2, right? We know the value of the current has been given as, that's 2 plus 4t, right? Integrating it with respect to time, right? Now the integration of this function will be, it will be 2t with limits 0 to 2, and it will be 4t square upon 2 with the limits 0 to 2, right? The total charge flown in the wire will be delta Q, that's equal to 2 multiplied by 2, right? Plus 2 into 2 square, right? That's 8 plus 4, that's 12 coulombs, right? So 12 coulomb will be the total amount of charge flown through the wire for time t equal to 2 seconds, right? So this is one way, right? This is one method that we can use to solve this question, right? The another method, very important method, that is the graphical method, right? Using the graph, right? Or using the current versus time graph, right? We know that integral IGT is nothing with the limits T1 to T2. It represents the area under current time graph, right? Area under current time graph. And the area under current time graph gives the total charge flow. That's the delta Q, right? So if we find the area under the current time graph, we'll get the total charge flown through the circuit, right? Now you can see here, this is the current versus time graph, right? At time t equal to 0, the current through the circuit is 2 amperes, right? And after time t equal to 2 seconds, the current through the circuit is 10 amperes, right? Now we'll calculate the area under this graph, right? Area under this graph. The area under this graph will give us the total charge delta Q, right? This will give us the total charge delta Q. So delta Q here will be area under this trapezium. We know the area of the trapezium is nothing, half of sum of parallel sides, right? Half of sum of parallel side. This side and this side are the two parallel sides, right? For this trapezium. And the length of this side is 2. And the length of another parallel side is 10, right? So it will be 2 plus 10, right? Multiplied with the distance between them. The distance between them is equal to 2, right? We'll multiply it here with 2. 2 into will get cancelled. We'll be left with 12 coulombs. So this is how we can find the charge flown through the circuit. Either we can go by the integration, right? Or we can calculate the charge flown through the wire of the circuit using the graph, right? So area under the current time graph gives the total charge flown, right? So these are the two methods, two ways to find the total charge flown through the circuit, right? Now let's move on to the next question, right? Let's move on to the next question. The question is that a potential difference applied to the ends of a wire made up of an alloy, right? Drives a current through it. The current density varies as 3 plus 2r, right? Where r is the distance of the point from the axis, right? If capital R be the radius of the wire, right? Then the total current through any cross section of the wire is. So the question is that let's suppose this is the wire, right? This is the cylindrical wire, right? This is the cylindrical wire. The current density is given as a function of radius r, right? That's J is equal to 3 plus 2r, right? This is the current density, right? This is the current density as a function of r, right? We have to find the total current through the cross section of this wire, right? The radius of this wire is given as capital R. This is the capital R, right? And the small r is the distance of this distance of the point from the center of this wire, right? We know that current is nothing, it's integral of current density dotted with the area, right? Now, if we integrate this function, right, if we integrate this, we'll get the total current between 0 to r, right? Now, we'll integrate it from 0 to r, right? Now, area of cross section is along the direction of the current density, right? It means the dot product between them will be, that will be j ta cos of 0 degree, right? Cos 0 is nothing, that's 1, right? The limit 0 to capital R, right? The limit 0 to capital R, this will be the total current here, right? And the current density as a function of R is given as 3 plus 2R. And the area of the cylinder will be given as 2 pi R dr, right? This will be the area of this cross section, right? So now integrating it with the limit 0 to R, right? We'll get, taking 2 pi as outside, it's a constant, right? It will be integral of 3R plus 2R square, right? 2R square dr, right? With the limits 0 to R, right? So this current, total current here will be 2 pi times the integration of 3r will be 3r square upon 2, right? 3r square upon 2 with the limits 0 to capital R, right? And the integration of 2r square will be 2r cube upon 3, right? 2r cube upon 3 with the limits 0 to r, right? And this will be the integral, right? This will be the total current. Now, putting the limits to this function, right? We'll get 3r square upon 2, right? Plus 3r square upon 2 plus 2r cube upon 3, right? 2r cube upon 3. So this will be the total current, right? This will be the total current flowing through this. This will be the total current flowing through this cylinder, right? Or cylindrical wire. So this is the total current. I is here the total current. And this current we have to find. So if we have been given a current density as a function of R, then how we can calculate the current through the wire or the current through the conductor? We have to calculate this function, that's integral of J dot dA, where J dot dA, J is the current density, right? Current density vector, and A is the area vector, right? Now let's move on to the next question here. The question is a current I flows through a uniform wire of diameter d, then the electron's drift velocity is v, right? The same current will flow through a wire of diameter d by 2 of the same material. The drift velocity of the electron in second wire is, right? Now the question is related to the drift velocity, right? We know that drift velocity is nothing. Drift velocity as a function of current, right? Or the relation between the drift velocity and the current is nothing. I is given as v t, right? V d a n e, right? Where v is the drift velocity, a is the area of cross section, n is the number density of electrons, and e is the charge of electron. So from here the velocity will come out to be a upon a n e, I upon a n e, right? Where I is the current flowing through the conductor. Now the same current is flowing through the through both the conductors, right? It means I will be constant here. We can replace, we can write it as I upon area of cross section will be pi r square, or we can write it as pi d square, right? Multiplied with the factor 4 here, right? And multiplied by e, right? So this will be the this will be the drift velocity, right? This is how we can represent the drift velocity in terms of the diameter, right? Now there are two materials. One is having a diameter of d, another is having a diameter of d by 2, right? D by 2. So it means that v1 will be equal to I upon pi d square ne, right, multiplied by 4, and V2 here will be equal to 4 times I upon pi. Now the diameter is half of the d, right? That will be t square n into e multiplied with the factor 4, right? So the drift velocity of the second conductor will be equal to 16 times I upon pi d square ne, right? Pi d square ne. Now calculating the ratio of the two drift velocities, V2 upon V1 will be 16 upon 4. That will be equal to 4:1, right? So this will be the ratio. This will be the ratio between the drift velocities or the drift velocities between in the two wires, right? Or we can see the drift velocity in the second wire will be the 4 times the drift velocity in the first wire, right? So this is how we can calculate the drift relation between the two drift velocities in a conductor, right? Now let's move on to the next question, right? So question number 4 says that a copper wire of length r and radius r is nickel plated, right? Till its final radius is 2r, right? The question is like this. Let's suppose this is the copper wire, right? This is the copper wire, and it has been nickel plated, right? This is the plating of the nickel, right? This is the plating of the nickel. This wire has been nickel plated, right? This wire has been nickel plated till final radius becomes 2r. So from here to here, the radius is 2r, right? And the radius of the copper wire is r, right? And the length, the total length from here to here is L, right? That's L. Now, if the resistivity of the copper and nickel are rho Cu and rho Ni, then find the equivalent resistance of the wire, right? We have to find the equivalent resistance of the wire. Now you can see here both these wires, copper wire and the nickel wire, right? They are connected end to end, right? They are connected end to end. It means the potential difference between the two ends of the copper wire and the nickel wire will be same, or we can say the nickel wire and the copper plating here will be they will be parallel to each other, right? They will be parallel to each other, right? It means the equivalent resistance will be nothing. It will be R copper multiplied by R nickel upon R copper plus R nickel, right? R nickel. Now we have to calculate these values RCU and RNI, right? Now talking about the RCU will be nothing. It will be the resistivity of the copper wire multiplied by the length, that's L, upon the area of cross section. Now the area of cross section of the copper wire is pi r square, right? Now calculating the resistance of nickel wire, it will be resistivity of nickel wire, that is rho Ni multiplied by the length. Now the area of cross section of the nickel wire will be this area, right? This area only, right? This area will be the area of cross section of nickel wire. That will be equal to actually the total area of cross section, that will be uh, 4 pi r square, right? Minus the area of cross section of this copper wire, that's pi r square, right? So final resistance of this nickel wire will be rho nickel L multiplied by upon 3 pi r square, right? This will be the final resistance, right? Now we can just substitute the values of RCU and RNI in this equation to calculate the total resistance or the equivalent resistance of this circuit, right? Or equivalent resistance of this conductor, right? That will be RCU multiplied by RNI, right? Upon RCU plus RNI. So the point here was that the area of cross section of this nickel, right? The total area of cross section of this nickel will be the total area of cross section of a large circular portion minus the area of cross section of the copper portion, right? That will give us the area of cross section of the nickel plated, right, region till point 2, right? So this is the total resistance or the equivalent resistance of this conductor, right? Now we have the similar question here once again. We have been given current density as a function of R, right? As a function of R, we have to calculate the total current, right? We have to calculate the total current. So the total current here will be nothing. We will just once again integrate this current density, right? We'll just integrate this current density to calculate the total current. So I will be equal to integral of J dot TA, right? With the limits 0 to capital R, right? 0 to capital R. Now the value of J is given as J naught 1 minus R upon R, right? Now dA will be nothing. It will be 2 pi R TR, right? 2 pi R TR with the limits 0 to capital R, right? 0 to capital R. So I here will be equal to J naught, right? J naught 2 pi will be outside of the integral, right? We'll be left with r minus r square upon r, right? Multiplied by factor dr, right? Now integrating it with 0 to r, right? So it will be 2 pi j naught, 2 pi j naught. It will be r square upon 2, right? With the limits 0 to r, right? Minus r cube upon 3 capital R with the limits 0 to r, right? So current here will be 2 pi j naught with the limits r square upon 2 minus r square upon 3, right? It will be r square upon 3, right? R square upon 3. So we'll get the value here j naught times 2 pi. So it will be 1 by 6, right? 1 by 6 and factor of r square in the numerator, right? The final answer here is it will be j naught pi r square, right, upon 3. So pi r square is nothing, it's the total area, right? It's the total area of cross section of this wire, right? That's equal to A. So in terms of area of cross section A, I will be equal to J naught A upon 3, right? J naught A upon 3. So this will be the total current flowing through this conductor, right? The total current through the conductor is J naught A upon 3. So this is how we can calculate the total current, right? Using the or integrating the current density with respect to R, right? Now let's move on to the another question, right? It's a very important question. Now you can see here a time varying current I is passed through a resistance R as shown in figure, right? Time as a function, current as a function of time is given in this graph, right? Or in this diagram. The resistance of the conductor is R, right? We have to calculate the total heat generated in the resistance, right? We know the total heat generated in any circuit or in any resistance is nothing, that's given as heat H. Heat H is equal to integral of I square R dt, right? So integrating the power with respect to the time will give us the total heat generated with the limits T1 to T2. So this is the equation we'll be using for the heat generation, right? Heat generation. This will be the equation we'll be using to calculate the total heat generated. Now you can see here from 0 to T naught here, from 0 to T naught, it's a function of time, right? It's a straight line here from 0 to T naught, or we can write this from 0 to T naught. The current I between 0 to t naught will be written as the slope of this straight line here is nothing, that is 3 I naught, right? The slope of this is 3 I naught upon t naught, right? That will be 3 I naught upon t naught. This will be the slope, right? And multiplied by the time t, right? And the intercept here is 0, so we'll add 0 to it, right? And the rest of the currents are constant here, right? Rest of the currents are constant here. So we have to integrate this portion first. We'll integrate it from 0 to T naught first, right? To calculate the heat. Let's suppose the heat generated is H1, and this heat will be nothing. It will be integral of I square R dt. That will be 3 I naught upon T naught, right? Multiplied by T whole square R into T with the limits 0 to T naught, right? 0 to T naught. So this will be equal to 3 I naught, it will be 3, that will be 9 I naught square upon T naught square, right? Integral of T square R dt, right? We'll just take R outside the integral, right? Dt, right? With the limits 0 to T naught, right? With the limits 0 to T naught. So we'll get here, the answer will be 9 I naught square, right? R upon T naught, we'll get T naught cube upon 3, right? T naught cube upon 3, right? So from here, 3 and 3 will get cancelled, and T naught and T naught will get cancelled. So we'll get the value of H1 here, 3 I naught square, 3 I naught square R multiplied by T naught square, right? So this will be H1, right? This will be the value of H1. Now calculating the value of H2. So H2 will be nothing, it will be I square RT, right? And because here the current from T naught to 2T naught is constant current, right? From T naught to 2T naught, the current is constant, and again from 2T naught to 3T naught, the current is constant. So H2 heat will be nothing. It will be I square R delta T, right? I square R delta T. So H2 here will be nothing. The current will be 3 I naught square, that will be 9 I naught square, right? 9 I naught square R delta T, 2 T naught minus T naught, that will be T naught, right? And similarly, H3 will be equal to I square R delta T, right? And the value of I from 2T naught to 3T naught is I naught, that will be I naught square R delta T, that's once again T naught, right? The total heat generated, it will be nothing, it will be H1 plus H2 plus H3, right? This will be the total heat generated in the circuit, right? This will be the total heat generated in the circuit or in the conductor, right? That will be equal to, so it will be 3 I naught square, 3 I naught square, 3 I naught square plus 9 I naught square, that's 12 I naught square, right? 12 I naught square and plus I naught square, right? That's 13 I naught square, right? That will be 13 I naught square R T naught, right? So this will be the total heat generated in the circuit, right? In the circuit or in the conductor from time 0 to 3T naught, right? This will be the total heat generated, right? So the heat generation will be calculated by using the integral I square RT, right? Through the circuit. So this is a very important question, right? Very important concept, right? To calculate the heat generated through the circuit, right? Now let's talk about the question number 6, right? The question number 6 is that IV curve has been given where to find the ratio R1 R2, right? We know that the current versus time graph or the voltage versus according to Ohm's law, V upon I is R, right? That's equal to R, or the V versus VI, slope of VI graph will give us the resistance, right? This will give us the resistance, right? This will give us the resistance R, right? Now if the characteristic graph is between current and voltage, right? IV graph, right? This will give us the 1 upon slope, right? The slope of this IV characteristic will be nothing, it will be reciprocal of the resistance, that will be 1 upon R, right? It will be the reciprocal of the resistance. Now the question here is given as I versus V, right? So we have to compare the resistances between the two graphs, right? So here for this first graph, right? For the first graph and the second graph, for the first graph, you can see here the angle here is 60 degree, or the slope here is tan 60, and tan 60 is nothing. That's equal to root 3, and that will be equal to, let's suppose that is 1 upon R1, right? That's 1 upon R1. And tan of 30 degree will be nothing. That will be equal to 1 over root 3. That will be equal to 1 over R2, right? 1 over R2, right? Now we have to calculate R1 ratio R2, right? R1 ratio R2. It will be 1 upon R2, 1 upon R1, right? That will be equal to 1 over root 3, right? Over root 3, right? So that will be equal to 1 over 3, right? So this will be the ratio between R1 and R2, right? So the slope of IV graph gives the reciprocal of the resistance, and the slope of VI graph gives the resistance of a conductor, right? Now, in the question number 7, you can see here, the question number 7 says that in the shown VI characteristics or in the shown VI curve, what will be the relation between R1, R2, and R3? You can see here the slope of R1 here is the slope of VI characteristics gives us the resistance of a conductor, right? Now you can see the slope of R1 here is greater than the slope of R2, right? Let's suppose this is theta 1, right? Let's suppose this is theta 1, this is theta 2, right? And this is theta 3, right? Now the slope here will give us tan of theta will give us the resistance, right? It will give us the resistance of the conductor, right? Or we can say tan of theta 1 is greater than tan of theta 2. That's greater than tan of theta 3, right? And from here, R1 will be greater than R2 will be greater than R3, right? So the correct option for this question will be option number 2, right? That's the correct option, right? Now let's focus on the question number 3, right? 3 copper wires have their lengths in the ratio 5 ratio 3 ratio 1, and their masses are in the ratio 1 ratio 3 ratio 5, right? Their electrical resistance will be in the ratio, right? We know that the ratio or the resistance of a conductor is given by resistance of a conductor is nothing, that's given by uh, R, that's equal to rho L upon A, right? So resistance of a conductor depends upon the length of the conductor and the area of cross section of the conductor, right? If we increase the length of a conductor, the resistance will increase. If we decrease the area of cross section of the conductor, the resistance is going to increase, right? Now, The three copper wires are having their lengths in the ratio 5:3:1, right? And their masses are in the ratio 1:3:5, right? But there is no factor of mass here, right? What we can do is that, let's suppose this is the conductor, right, of length L, right, of length L, and the area of cross section A, right? To calculate the volume of this conductor, that will be area of cross section multiplied by the length of this conductor, right? If we multiply denominator by the length and in the numerator as well, we will get R equal to rho L square upon A into L, right? A into L is nothing, it's the volume of the conductor, right? AL square upon V, right? We know the density D is nothing, it's defined as mass per unit volume, right? Or we can define this volume as density upon mass, right? Density upon mass. So from here, we'll get the resistance as rho L square. Replacing the volume by density upon mass, that will be density multiplied by the mass. Now I have written the resistance in terms of the density and the mass, that's rho L square multiplied with the mass of the conductor upon the density, right? Now you can see here the resistance actually depends upon resistance actually, sorry, density is actually equal to mass upon volume, right? And the volume will be equal to mass upon density, not density upon mass, right? It will be mass upon density, right? So there will be factor density in the numerator, right? T, and mass in the denominator, right? Right. So from here you can see here the resistance is directly proportional to the L square upon M, right? So now calculating the ratio, so ratio R1, ratio R2, ratio R3, it will be depend upon the L square, right? The L square is 25, right? So the first factor here is 5, it will be 25, right? 25 ratio 1, right? The second is uh, 3, that will be 9 ratio 3, right? And the third is uh, 1, that will be 1 ratio 5, right? So this will be the ratio between the R1, R2, R3, right? Now simplifying it, we'll multiply by a factor of 5 in the numerator, we'll get it equal to 125 ratio 3 ratio 1, right? So this will be the final answer for the resistance or the ratio of their electrical resistance, and will be in the ratio 125 ratio 125 ratio 15, not 3, 125 ratio 15, right? It will be 125 ratio 15 ratio 1, right? So the option C will be the correct option, or the option 3 will be the correct option for this question, right? Now let's move on to the next topic, right? Now let's discuss about the percentage change in the conductor, right? Percentage change in resistance in the conductor, right? You can see here, let's suppose we have this conductor of length L, right? The length of this conductor is L and the area of cross section of this conductor is A. Then the resistance of this conductor is given by rho L upon A, right? Resistance of this conductor is given as rho L upon A. So this is the resistance of the conductor. Now changing the length of the conductor will change the resistance. Changing the area of cross section of the conductor will change the resistance of the conductor, right? Now let's focus on how percentage change in a resistance actually changes by changing the resistance, by changing the length or the area of cross section. Now you can see here, if percentage change is less than 5%, right? If percentage change is less or equal to 5%, then we'll be applying this concept, right? This concept that delta R upon R, that's the percentage change in the resistance, will be actually equal to 2 times delta L upon L. If there is some percentage change in length, and then twice that will be the percentage change in resistance, right? Similarly, if there is some percentage change in area of cross section, right? Percentage change in area of cross section, then twice uh, delta A upon A multiplied by 100 will be the percentage change in uh, resistance, right? Similarly, if we have some percentage change in radius, right? Then we'll have 4 times delta R upon R multiplied by 100, right? So the percentage change in resistance will be 4 times, right? The percentage change in the resistance will be 4 times, right? Now we know upon stretching, if we stretch a conductor, right? Upon stretching a conductor, right? Upon stretching a conductor, the length of the conductor increases, but the area of cross section of the conductor decreases, and the radius of the conductor also decreases, right? Now, resistance of the conductor is proportional to the L square upon stretching, right? It's proportional to the N square, L square upon stretching, right? So if we stretch, if we double the length of the conductor, right? If we double the length of the conductor, then the resistance will become, if the new length of the conductor is twice the previous length, then the new resistance will be nothing. It will be 4 times the old resistance, right? Similarly, so it will depend upon the factor of L square, right? It will depend upon the factor of L square, right? So it means that if we do a if a resistance of if the length of the conductor is made n times, then the new resistance will be n square times the older resistance, right? This is a frequently asked question. If the length of the conductor is made 3 times, then the resistance will become, it will become 9 times. If the length of the conductor is stretched by 4 times of its initial length, then the new resistance will become 16 times, right? It will become 16 times. Similarly, if the radius of this conductor is actually upon stretching, it decreases to r naught by n, right? It decreases to r naught by n. And the radius of the conductor upon stretching, right? Upon stretching a conductor, if the radius of the conductor becomes r naught by n, then the new resistance will become n to the power 4 times the older resistance, right? So n to the power 4, right? So the factor 4 will be there, right? You can see here with respect to resistance, we have the factor 4 here. If there is a change in radius, right, then it will be 4 times the change in resistance, right? So n to the power 4 will be the new resistance, right? If we decrease the radius of this conductor to r by n, right? R by n. So similarly, if we increase the radius of this conductor n times, right, upon n times, it means increase in radius, right? Increase in radius. Then the resistance is going to decrease, right? Then the new resistance in that case will be nothing. It will be r naught upon n to the power 4, right? This will be the new resistance in that case, right? So the new resistance in that case will be r naught upon n to the power 4, right? So this is with respect to the percentage change in resistance, or what is going to happen to the resistance if the length of the conductor is doubled, right? What's going to happen to the resistance if the radius becomes r naught by n, right? It will become n to the power 4, right? So this is how we can actually, now it's only upon stretching, right? There's a concept we have used that if we stretch the same material, now if the stretching word is not used, or there is no such type of stretching, and if we double the length of the conductor, right? By not stretching, let's suppose we have the two conductors, one of length L, another conductor of length 2L. Then the second conductor will have the resistance twice the previous conductor, right? So you have to keep this thing in mind, whether there's a stretching happening or not, right? Otherwise, the things will be different, right? Now, with respect to the same concept, right? Percentage change in resistance, how will we calculate the a wire is stretched by 30% of its original, right? Find percentage change in percentage increase in resistance or percentage change in resistance, right? Now we cannot use this equation, right? Let's suppose most of the students, what they do is that they use this equation, that delta r upon r multiplied by 100, right? What they will do is they will use this equation 2 times delta l upon l multiplied by 100, right? So they will substitute the value of this percentage change is 30%, and according to them the final answer should be 2 into 30, that's 60%. But this is incorrect, right? This is incorrect, right? Because we know that this can be only used, we can directly use this equation only when there is a percentage change if percentage change is less or equal to 5%, right? Less or equal to 5%. You can see here I have clearly mentioned it. Use this equation only when there is a percentage change in length or the radius or the area of cross section less or equal to 5%, right? So this answer is not correct. This is incorrect, right? This is incorrect. This is incorrect, right? This is not a correct answer, right? So how will we find the percentage change in the resistance, right? We know that R is directly proportional to L square, right? It's L square upon stretching, right? Proportional to the L square, right? It's proportional to L square. Now you can see here, if the length has been stretched by 30%, it means the new length will be 1.3 times the older length, right? So it means that R2 upon R1 will be nothing. It will be equal to L2 upon L1 ka whole square, right? That's equal to 1.3 L upon L whole square, right? That's nothing. That's 1.69, right? That's 1.69. That's R2, right? Now um, uh, you can see here, the new resistance has actually increased by a fraction of 0.69, right? the new resistance has actually increased by a fraction of 0.69, right? So 0.69 multiplied by 100, it's nothing, it's the 69%, right? It's the 69%. So the correct answer to this question is nothing, that's the 69%, right? 69% is the answer. So what you will do in your exams, if such questions are asked, let's suppose you are asked 30% increase, what we will do is that you will just do 1.3 whole square, that's 1.69, right? 69% is the answer, right? Similarly, if you are given the 40% is their increase, what you will do is or 20% is the increase, what you will do, it will be 1.2 whole square, that will be 144, right? Because 12 square is 144, it will be 1.44. The percentage change in resistance is 44%, right? 44%. And similarly, if there is a 10% increase in the length, then what you will do is 1.1 whole square, that's nothing, 11 square, that is 121, right? 1.21, it means that 21% is the percentage change in resistance, right? 21% is the percentage change in resistance. That's how you can solve this question, right? That's how you have to solve this question, right? So you have to keep in mind whether the percentage change is less than 5% or it's greater than 5%, then accordingly we have to. Generally, you can use this equation. You can use this equation up to 10%, right? Up to 10%. But beyond 10%, this is not applicable, right? This is not applicable. We have to go by our usual ways or usual methods to find the percentage change in the resistance, right? Or any physical quantity, right? Question number 10. Well, let's focus on the question number 10. A wire is stretched so that its radius is increased by 3%. Now you can see here the 3% is actually less or equal to 5%. So we can use those equation directly, right? So it is stretched, it's decreased by 3%. We know with respect to radius, this equation we have to use, right? This is the equation we will be using with respect to the radius, right? It means that delta R upon R multiplied by 100, that will be the percentage change in resistance, right? Percentage change in resistance, right? This will be the percentage change in resistance, right? If this is the percentage change in resistance, right? So what we'll be doing, it will be 4 times delta R upon R multiplied by 100, right? Multiplied by 100. Now the percentage decrease in the resistance is 3%. So 4 multiplied by 3 is nothing. That's the 12% is the answer, right? So 12% will be the percentage or the percentage error or the percentage change in resistance, right? So 12% will be the percentage change in resistance. Now let's move on to the question number 11. The length of the conductor is doubled and its radius is halved, its specific resistance is. We know the specific resistance is nothing. This is the resistivity, right? The resistance of a conductor is given by rho L upon A, or the resistivity of this conductor is Ra upon L, right? Ra upon L, right? The specific resistance means L is equal to 1 unit, right? L is equal to 1 unit, and the area of cross section is nothing. That's 1 unit square, right? It's 1 unit square. 1 unit square is the area of cross section. So this is the specific resistance, right? We have specified the area of cross section for this resistance, and we have specified the length of this conductor as well. It means that the specific resistance will be independent of the length of the conductor. It will be independent of the area of cross section of the conductor. So upon changing the length, even if we double the length of the conductor, the specific resistance is not going to change. It will remain unchanged, right? Similarly, on the same question, there was a question asked in JEE mains. JEE mains in the January session, right? In the January session, the same type of question was asked, right? With a different language altogether, right? So we'll be discussing that question as well, right? A wire of length L and resistance R is cut into 4 parts. Each 3 parts are placed in parallel, and 4th part is placed in series with the equivalent resistance will be, right? Now the question number 12 says that a wire of length L and resistance R is cut into 4 parts, right? We have this wire of length L, right? Its resistance was R. We have cut this into 4 parts, right? We have cut this into 4 parts. 3 parts are placed in parallel and the 4th part is placed in series with the equivalent, right? It means that the 3 parts are placed like this, right? The 3 parts are placed like this, and the 4th part is placed in series with them, right? Like this. So this is actually the uh, arrangement of these wires, right? Arrangement of these links, right? Let's suppose if the resistance of this total wire is L, right, of length L, we have uh, cut it into 4 parts, L by 4, L by 4, and L by 4, right? So if the length of the length of the conductor becomes 1 by 4, right? We're not doing any stretching here. We're just cutting the conductor, right? It means that the new resistance of each conductor will be R by 4, right? It will be R by 4, right? So the resistance of this conductor will be R by 4. It will be R by 4 here as well. It will be R by 4 here as well. And this resistance will also be R by 4. Now now calculating the equivalent of these three resistors, right? These equivalent of these three resistors, they are in parallel, right? And we know when n number of equal resistors are parallel, right, then the equivalent resistance will be R upon n, right? So their equivalent will be R dash, that will be R upon 4, right? They are 3, so it will be R upon 12, right? R upon 12. So these three resistors will have equivalent resistance equal to R upon 12. We have this R upon 4 here. Now these two resistors R upon 12, right? R upon 12 and R upon 4 are now in series with each other, right? If they are in series with each other, the equivalent resistance will be nothing. It will be the R upon 12 plus R upon 4, right? R upon 12 plus R upon 4. So the R equivalent is nothing. That's equal to R equivalent is nothing. It's equal to 4R upon 12, right? That's equal to R upon 3, right? So this is the final equivalent resistance of this arrangement, right? So this is the equivalent resistance of this arrangement, right? Now let's talk about the question number 13, right? Question number Talking about the question number 13, let's the two wires of equal diameters, right? Of resistivities rho 1 and rho 2, right? We have two wires. We have two wires of equal diameters of resistivities rho 1 and rho 2 and lengths L1 and L2, right? So it means these are the two wires, right? They are joined together, right? Two wires have been joined together. The wire 1 has resistivity rho 1 and the wire 2 has resistivity rho 2, right? The length of the first wire is L1, the length of the second wire is L2, and their area of, since they are joined together, they have same diameter. It means their area of cross section should be same, right? They will have the same area of cross section A, right? Now the question is asking find the equivalent resistivity of the combination, right? Equivalent resistivity of the combination. It's a very important question, right? Equivalent resistivity of the combination, right? So this, let's suppose this is the equivalent conductor for these two conductors, right? Its area of cross section will also be same, that's A, and it will have a length equal to L1 plus L2, right? It will have a length equal to L1 plus L2, right? And the resistance, let's suppose the resistance of this conductor is equal to R equivalent, right? R equivalent, right? Since these two conductors are in series with each other, right? They are in series with each other. The total resistance R equivalent will be nothing. That will be R1 plus R2, right? That will be R1 plus R2. That's the R equivalent, right? So the equivalent resistance of the two resistors will be R1 plus R2, right? That will be equal to rho 1 L1 upon A, right? Plus rho 2 L2 upon A, right? Rho 2 L2 upon A, right? This is the equivalent resistance of these two resistors, right? So it's rho 1 L1 upon A plus rho 2 L2 upon A, right? Now the area of cross section R equivalent will have the same area of cross section and the length L1 plus L2. So we can write it as rho equivalent. The length is L1 plus L2, right? Upon area of cross section A, right? That will be equal to rho 1 L1 upon A1, right? Plus rho 2 L2 upon A2, right? A. Now A and A will get cancelled. Will be left with the final answer here. The rho equivalent or the equivalent resistivity of these two combination will be rho 1 L1, rho 2 L2 upon L1 plus L2, right? So this will be the final equivalent resistivity of this conductor, right? The equivalent resistivity of this conductor will be rho L1 plus rho L2 upon L1 plus L2, right? This is the equivalent resistance of this conductor, right? Now let's move on to the another question, right? Very important question, frequently asked question in different exams, be it NEET, be it JEE, right? Very frequently asked question, right? The network we call as ladder network or the infinite series network, right? So you can see here the equivalent resistance of the following infinite network of resistance is, right? You can see here this network actually repeats itself up to infinity, right? The same type of network is repeated continuously up to infinity, right? Uh, we'll try to we'll try to solve this network, right? Let's suppose let's suppose the repetition of the network is from here, right? This is the repetition, right? After this point the repetition occurs, right? After this point the repetition occurs, and this repetition will also go to infinity. It means that we can just call this circuit also as R equivalent circuit, right? It will be R equivalent, right? It means that whatever be the equivalent about A and B, same will be the equivalent about C and D, right? C and D, right? So the equivalent resistance about C and D will be same as the equivalent resistance about A and B, right? So it means that uh, we'll have the equivalent circuit like this, right? So this is the R equivalent, right? This is the R equivalent, right? This is 2 ohm resistor. This is 2 ohm resistor, right? And it will have equivalent resistance about A and B, and that will also be equal to R equivalent, right? Now you can see here R equivalent and 2 ohm resistor are in series, so they will have a resistance equal to 2 plus R equivalent, and they will be in parallel with this, right? 2 ohm resistor. So the R equivalent will be nothing. It will be 2 multiplied by 2 plus R equivalent upon, right? 4 plus R equivalent, right? 4 plus R equivalent. So from here we'll get the equivalent resistance, right? Let's replace this R equivalent with R, right? So it will be R square plus 4 times R, right? That will be equal to 4 plus R, right? 4 plus R, right? That will be equal to 4 plus R, right? So it will be R square, right? R square plus 4R, R square plus 4R, that will be equal to 4 plus R, right? From here you can see here we'll have the final quadratic equation R square plus 3R minus 4, that will be equal to 0, right? So the R value will have value R equal to minus 3 plus minus under root of P square minus 4AC. B square is 9 minus 4AC, that is 4 into 4 is a 12, right? Upon 2A, right? That will be equal to 2, right? So the value of R here will be equal to minus 3 plus 9 plus 12, it will be 21, right? It will be 21. So 9 plus 12 is 21, right? Upon 2, right? Upon 2. So from here, this will be the equivalent resistance, right? Minus 3 plus root of 21 upon 2. This will be the equivalent resistance for this circuit, right? So this is how we'll use the how we will actually calculate the equivalent resistance of infinite ladder circuit, right? Now moving on to the question number 15 here, right? A uniform wire of resistance 18 ohm is bent in the form of a circle, right? Calculate effective resistance across points A and B. Now, a uniform wire of resistance given as 18 ohm, right? We have a uniform wire of resistance equal to 18 ohm, right? It's bent in the form of a circle. We have to calculate the effective resistance across the points A and B, right? Talking about the question number 15. A uniform wire of resistance 18 ohm is bent in the form of a circle, right? Calculate effective resistance across the points A and B. We have to calculate the effective resistance of the circuit across the points A and B, right? Across the points A and B, we have to calculate the effective resistance for the circuit, right? Now, the angle subtended by the points A and B at the center of the circle is 60-degree angle, right? Now, if the total resistance of this circle is 18 ohm, right, then the resistance for this 60 degree length for this length subtending 60-degree angle will be, it will be 18 upon 360 multiplied by 60-degree, right? So it means it will be upon 6, right? It will be equal to 3 ohm, right? It will be 3 ohm. So it means that resistance between A and B will be equal to 3 ohm, right? And the remaining resistance, that's 15 ohm, that will be between B to A, right? That's the 15 ohm resistor, right? Now you can see here 15 ohm and 3 ohm are in parallel to each other. We can just put these two resistors in parallel to each other, right? 3 ohm and 15 in parallel to each other, right? So their equivalent resistance will be nothing. It will be 3 multiplied by 15 upon 18, right? So it will be 3 and 6, right? That will be equal to 5 upon 2, right? 5 upon 2, right? That's 2.5, right? 2.5 ohm. That's 2.5 ohm, right? Or 5 upon 6 or 2.5. Now let's move on to the question number 16, right? Let's discuss the question number 16 here. The question number 16 says that if circuit is short circuited, right? If the circuit is short circuited, let's give a brief about the short circuit, right? Let's give a brief about the short circuit, right? Let's suppose this is the resistor R, right? This is the resistor R, right? Resistor R. And let's suppose this resistance R has been short circuited between these 2 points, right? It has been short circuited between these 2 points A and B, right? It has been short circuited between the 2 points A and B, right? Between the 2 points A and B. By short circuiting, we mean that we are directly connecting A point with the B point, or we're connecting the two ends of the resistor with the same potential, right? If the potential at this point is V, then the potential at this point has to be V, right? It means that the potential difference VA minus VB will be equal to 0. If the potential difference between V and VB is 0, it means there will be no current flowing through this resistor, or whatever be the current through because of the source, that current will flow through this short circuited path. It will not flow through this resistor. It means that this resistor has no role to play here. We can just replace this resistor from the circuit, right? We can just replace this resistor from the circuit, and this is what happens in the short circuited circuits, or we can say this is the concept of the short circuiting the 2 points, right? Now the same concept will be applying here, right? Same concept will be applying here, right? If circuit is short circuited between A and B, then what will be this current supply by source, right? Then what will be the current supply by source? Now you can see here, uh, these 2 points have been short circuited, right? It means if these 2 points have been short circuited, connected by a connecting wire, the potential at A should be V, and the potential at B will also be V, right? It means that for this path, right, there is no potential difference between the two ends, right? So the VA minus VB is actually equal to 0, right? If the potential difference is 0, it means that the current flowing through this path has to be equal to 0. It has to be equal to 0. It means that we can just remove these two resistors from the circuit, or our equivalent circuit here will be nothing. This will be the equivalent circuit, right? This will be the equivalent circuit. That's R, and this is V. So the current through the source will be nothing, and the same whole current I will be flowing through this short circuited path, right? There will be no current through this path because of zero potential difference, or we have short circuited the 2 points, right? And the same current will flow like this, right? So this will be the path of the current, right? So there will be no current along this path. So the net current drawn by the battery will be V upon 2R, right? So this will be the net current drawn by the battery, right? Now, let's focus on the question number 17, right? So the question number 17 is once again based on the short circuiting of the circuit, right? Find out equivalent resistance between A and B. Now you can see here there's a circuit, right? This is a circuit. Where to find the equivalent resistance between the 2 points A and B, right? Now you can see here the potential at this point is, let's suppose V, then the potential at this point will also be V, right? And the potential at this point will also be equal to V, right? If the potential at this point is V, then the potential at this point is also V. The potential at this point is also V. Or we can say the potential difference across this resistor is actually delta V. That's the potential difference across this resistor is equal to 0. It means there will be no current flowing through this circuit, right? There will be no current flowing through this resistor, right? And similarly, if we look at this point, if the potential at this point is V, potential at this point is also V, and the potential at this point will also be equal to V. It means the potential difference across the 2 points of this resistor will also be equal to 0. It means that there will be no current flowing through this circuit, flowing through this resistor at all, right? So there will be current only going from here to here, right? Like this, and from here to here, like this, right? This is the path of the current, right? Or we can redraw this circuit like this. This is R, right? This is the R here. This is the resistance R. This will be another resistance R here. And we left with this resistor, right? R. I can see here, these two resistors are parallel to each other. Their equivalent will be nothing. That will be R by 2, right? R upon 2 and R is 0.8, this is point B. So the overall equivalent resistance for the circuit is nothing, it's 3R upon 2, right? 3 upon 2, 3R upon 2. So this will be the equivalent resistance of the circuit for equivalent resistance for this question number 17, right? Now let's talk about the current as a, or we can say the resistance of a conductor as a function of temperature, right? We know that resistance varies as a function of temperature, right? The resistance of the conductor actually increases upon increasing the temperature, while the resistance of the semiconductor decreases upon increasing the temperature, right? And the resistance as a function of temperature is nothing, that's RT, that's equal to R naught 1 plus alpha delta T, right? 1 plus alpha delta T. Here alpha is nothing, it's the temperature coefficient of resistance, right? It's temperature coefficient of resistance, right? It's the temperature coefficient of resistance, right? Temperature coefficient of resistance, or we can define this alpha as delta R upon R into delta T, or we can say it's the relative change in resistance per degree rise in temperature, right? It's the relative change in resistance per degree rise in temperature. And we know for conductors, resistance increase upon increasing the temperature, so alpha will be positive, right? And for semiconductors, the value of this alpha will be nothing, it will be negative, right? Value of alpha will be negative for semiconductors, right? For semiconductors, the value of alpha will be negative, right? Now let's calculate the value of resistance at 500 degrees centigrade. So R at 500 will be nothing, it will be R naught, that is 133. 1 plus alpha delta T. The value of alpha has been given as 0.0045, right, per degree centigrade multiplied by delta T. Delta T here is 500 minus 150, that's equal to 350, right? 350, right? So this is by computing this, you'll get to know about the final resistance, right? So the resistance will be R500, it will be actually greater than R150, right? It will be greater than R150. So this is how we can calculate the resistance of a conductor, right? As a function of temperature, right? Now let's move on to the question number 19, right? The question number 19 says that the lowest resistance which can be obtained by connecting 10 resistors, each having resistance 1 upon 10 ohm base, right? So it means that we have 10 resistors here. We have 10 resistors here, right? 10 resistors here, right? And each of resistor is having a resistance 1 upon 10 ohm, right? Now we know that in case of series combination, the total resistance of the circuit actually increases, right? In series combination of the resistors, the total resistance of the circuit increases. But in case of parallel parallel arrangement of the, or the parallel combination of the resistors, the total resistance of the circuit decreases, and it is always less than the least resistor circuit, least resistor resistance, right? Or we can say that, let's suppose we have three resistors, 1 ohm, 2 ohm, 3 ohm, right? Then the, if they are 1 ohm, 2 ohm, 3 ohm are placed in parallel to each other, and then the equivalent resistance will be less than 1 ohm, right? Similarly, if they are placed in series with each other, then the equivalent resistance will be 6 ohm, right? So you can say that the least resistance can also be only be obtained if we place all of them in parallel to each other, right? All of them in parallel to each other, right? Then we'll be able to obtain the least resistance, right? So it means that we have to put all these 10 resistors parallel to each other, right? All these 10 resistors parallel to each other, right? So it is 1 by 10, right? 1 by 10, 1 by 10, right? And the number of these resistors is 10, right? And we know that when n number of resistors are parallel to each other, where the resistance of each resistance is R, then the equivalent resistance is R upon N, right? R upon N. Similarly here, the R equivalent will be nothing, R upon N, that's the value of R is 1 upon 10, that's equal to 1 upon 100, right? 1 upon 100 ohm. So this is the least resistance that can be obtained here, right? Now let's move on to the question number 20, right? The question number 20 says that a battery of EMF 10 volt is connected to resistance as shown in figure, right? A battery of EMF 10 volt is connected to resistance as shown in figure. The potential difference VA and VB between the points A and B is, right? So you can see here, we have to calculate the potential difference between the 2 points VA and VB, right? Now let's suppose, let's just try to calculate the current drawn by the battery first, right? battery first. So the equivalent of these two resistors will be 4 ohm, and the equivalent of these two resistors will be 4 ohm, right? Right? So we can write this circuit as like this. This will be the equivalent circuit for this. This is 4, this is 4, this is 3, right? And there is a battery of 10 volts, right? Battery of 10 volts. This is the 10-volt battery, right? Now you can see here the current I is drawn from the battery, right? Now the equivalent of these two will be 4 upon 2, that's equal to 2, right? 2. So the equivalent circuit will be here once again. Uh, 2 and 3, right? That's 10 volt, right? So it means that the current through the circuit or current drawn by the battery, that's I, that's nothing, that's equal to 10 upon 5, right? 10 upon 5, that is equal to 2 amperes, right? So 2 ampere current is actually flowing through the battery, right? 2 ampere current, right? The 2 ampere current will be flowing through the circuit, right? And this 2 ampere current will reach this junction point. It will be distributed along two branches. One branch is this, another branch is this. It means that they are having the same resistance 4 ohm and 4 ohm, right? It means 1 ampere will be along this branch and 1 ampere will be along this branch, right? Now the current, let's suppose this is the point C here. Now VC minus VA has to be equal to I into R, right? I is here 1 and the resistance is 1. That will be equal to 1 volt, right? And similarly, VC minus VB here has to be equal to I into R. That's 3 into 1. That's equal to 3 volt, right? Now this is first equation first and this is our equation second. Now if we subtract first from second, we'll get VC minus VB minus Vc plus Va, right? That's equal to 3 minus 1, that's equal to 2 volts, right? So from here, Vc and Vc will get cancelled. We'll be left with Va minus Vb, that's equal to 2 volts, right? So this is the potential difference between points A and B, right? The potential difference between 2 points A and B is 2 volts, right? So 2 volt is the answer for this circuit, right? So the potential difference between point A and point B is nothing, it's 2 volts, right? But let's move on to the question number 22, right? The three equal resistors, each equal to resistance R, are connected as shown in the following figure, right? Then equivalent resistance between points A and B is, right? So you can see here the potential at this point is V. Let's suppose potential at this point is V. They are connected by a short. Then the potential at this point will also be equal to V, right? It means that they have the common point here. This is the common point. Let's suppose this is A. It means that this resistor R and this resistor R will be parallel to each other, right? And similarly, this also the common point, this and this potential is equal to this potential. So the potential here is also equal to V. It means all the three resistors are actually parallel to each other, right? All the three resistors are actually parallel to each other, right? They are parallel to each other. Each of resistance R and R and R, right? And we know their equivalent resistance will be nothing. It will be R upon N, right? That is R upon 3, right? R upon 3. So R upon 3 will be the equivalent resistance for these three resistors, right? Now let's move on to the question number 23. The current from the battery in circuit diagram shown is, right? The question asks that the current from the battery in circuit diagram shown is, right? So you can see here, let's suppose the current I is here, right? Now the current I will be nothing, it will be V upon R equivalent of the circuit, right? Now let's calculate the R equivalent of the circuit. So this is 7 plus 1, that's 8. 8 plus 10 is 18, right? 18 ohm resistor is in parallel. 18 ohm resistor. Let's cross this and place this 18 ohm resistor parallel to them, right? 18 ohm resistor parallel to them. So the equivalent of 18 and 6 is nothing. 6 multiplied by 18 upon 24, right? It will be equal to 9 upon 2. That's 4.5 ohm, right? That's 4.5 ohm, right? So 4.5 ohm is the equivalent resistance, right? Now the 4.5 plus 2 ohm plus zero point 0.5 ohm, right? That will be equal to that will be 5 plus 2 will be 7, 7 and 8 will be 15, right? That will be 15. It means the R equivalent here is nothing, that is 15 ohm, right? 15 ohm here is the R equivalent, right? The current here will be nothing. It's V upon R equivalent. That's 15 upon 15. The battery current drawn by the battery is nothing. That's equal to 1 ampere, right? So 1 ampere current will be drawn by the battery through the circuit, right? Now let's discuss this question, right? It's a very important question, right? A wire of a resistance 4 ohm is bent in the form of square. Determine the equivalent resistance between two adjacent corners of the square, right? So let's suppose we have wire, right? We have wire, right, of length L, the wire of length L, and the resistance of this wire is 4 ohm, right? Now this wire has been bent like this in the form of a square, right? So each of side and A, right? It means that this L must be equal to 4A, right? Or we can say A is equal to L upon 4. So the length of each wire is 1/4 of the previous length, right? So it means that the resistance of this wire will be also equal to R by 4, right? It will also be equal to R by 4, right? It will be also equal to R by 4, right? R by 4, R by 4. Or we can say that we can redraw this circuit like this. These are four resistors. These are four resistors. R by 4, R by 4, R by 4, and R by 4, right? And we have to calculate their resistance, equivalent resistance across adjacent corners, right? Adjacent corners. So it means, let's suppose this is point A, this is point B. Across these points, we have to calculate the equivalent resistance, right? Now you can see here, this resistor and this resistor will be in series. This and this will be in series, right? So their equivalent resistance will be nothing. It will be R upon 2, right? That will be in parallel with R upon 2, right? That will be in parallel with R upon 2, right? Now their equivalent resistance will be nothing. It will be R upon 2 multiplied by R upon 2, right? Upon R, right? That will be upon R, right? So their equivalent R equivalent here will be nothing. It will be R upon 4, right? R upon 4. So R upon 4 will be the equivalent resistance for the circuit, right? So R upon 4 is the equivalent resistance for the circuit. Now let's talk about this question, right? The electric current through a wire varies with time as I naught plus BT. This question was asked in JEE mains, right? In the January session, JEE January session, right? In this session, right? Similar question was asked in January JEE, right? 2024, right? This question was asked in January session, right? In one of the shifts, right? In one of the shifts. The electric current through a wire varies with time as I naught plus BT, where I naught is equal to 20 ampere and B is equal to 3 amperes. The amount of electric charge cross through a section of the wire into 20 sequences. And we know that we also discussed that amount of charge we can calculate either by using the graph or by integrating the current versus current with the time, right? So it will be integral of ITT with the limits. Uh, for 20 seconds, it will be 0 to 20, right? 0 to 20. Now the value of I is given as I naught plus beta t, right? Beta t dt with the limits 0 to 20, right? 0 to 20. So the total charge delta Q here will be I naught t, right? I naught t with limits 0 to 20, right? Plus eta t square upon 2, right? With limits 0 to 20, right? Now let's substitute the values, right? It will be 20 I naught, right? 20 I naught plus it will be 20 square, that's 400 upon 2, that's 200, right? 200 beta. 200 beta. Now let's put the value of I naught and beta here. The value of I naught is given as 20, so it will be 400, right? 400, and the value of beta is given as 3 ampere per second. That will be 200 multiplied by 3, that will be 600, and the final answer will be 1000 coulombs, right? So the amount of charge flown uh, during this time, right, is nothing, it's 1000 coulombs, right? So 1000 coulombs will be the answer, right? 1000 coulomb will be the answer for this question, right? Now let's talk about the question number 25, right? Question number 25. Question number 25, it's the same question, similar question we discussed before also, right? And the same type of question was asked again in the JEE mains, right? In the January session, right? Wheatstone bridge principle is used to measure the specific resistance of a given wire, right? Having length L, radius R. If X is the resistance of wire, right? If the length of the wire gets doubled, then the value of specific resistance will be. We know that value of specific resistance, right? Specific resistance rho is, it's nothing, it's RL upon A, right? So for the specific resistance, L should be 1 unit, right? And A should be equal to 1 unit square, right? So 1 unit square. So it's a specific resistance. The rho only depends on temperature, only depends on temperature and nature of material. Depends on temperature, only depends upon temperature and nature of material, right? It only depends on temperature and nature of material, right? It only depends on temperature and nature of material, right? So resistivity of a conductor will only depend on temperature and nature of material. It will not depend on length and area of cross section. So if the length of the wire gets doubled, then the value of specific resistance remains same, right? It remains same, right? That is, the answer will be S1, right? The answer will be S1, right? So it will not change, right? It will not change. Now let's discuss the final question of this session, right? This is the current electricity part one, and the part second will be discussed in the next session, right? It will be discussed in the next session, right? This is the question number 21, right? The question number 21 says that if potential difference V is given as 200 plus minus 5 volts, right? And current through the resistor is given as 20 plus minus 0.2 amperes, right? This is the current. And this question is also asked in JEE January session, right? Jan session, right? Find percentage error in resistance, right? We have to find the percentage error in resistance, right? The percentage error in resistance is delta R upon R multiplied by 100, right? That will be equal to, we know V is equal to IR, right? V is equal to IR, or R is equal to V upon I, right? V upon I. So from here, delta R upon R will be equal to delta V upon V, right? Delta V upon V multiplied by 100, right? Plus delta I upon I multiplied by 100, right? We can see here, the delta V here is given as 5 volts, right? It's 5 volts, and delta I is given here as 0.2, right? So delta V is 5 and V is 200, that's 500 upon 200 multiplied by 100 plus delta I is 0.2 upon 20 multiplied by 100, right? Multiplied by 100. So it will be 5, right? 2, that's 2.5, right? 2.5, right? Plus 5 to 10, that will be 1, right? That will be equal to 3.5%, right? So the percentage change in resistance, that's delta R upon R multiplied by 100, that's nothing, that's 3.5%, right? That's 3.5%. So 3.5% will be the percentage error in resistance, right? So this is how we can calculate the percentage error in resistance, right? If the data for the voltage and current electricity or the current I is given, right? This is how we can find the percentage change in resistance, right? So we'll stop here, right? That's it for today. In the next session, we'll be discussing a few more questions, right? And that will be purely based on the rest of the topics of current electricity. That will be based on uh, cells, that will be based on Kirchhoff's law, right? That will be based on power, right? And that will be based on different electrical devices, right? So we'll stop here. We'll meet in the next session. Till then, take care and goodbye.